Today's topic is elements of transport layer. The elements of transport layer are addressing, connection establishment, connection release, flow control and buffering, multiplexing, and crash recovery. The transport services is implemented by transport protocol used between the two transport entities. The transport protocol reassembles the data link protocol. Significant differences are present due to the major dissimilarities between the environment in which the two protocols operates. Protocols are similar to data link layer and the transport layer like flow control, congestion control, etc. It provides same functions, but figure 1 represents the elements of data link layer which shows the physical connection between the two routers. Here, the dealing with the connection is easy. In the second figure shows the control of flow between two hosts, that is between two subnets or routers and various connections. This becomes somewhat tricky. The physical channel exists in data link layer, whereas in transport layer it is replaced by the entire subnets. And in data link layer, there is no explicit addressing of destination, whereas in transport layer, it requires explicit addressing of the destination. And coming to the buffering and the flow control, both are needed in both layers. But the presence of a large and dynamic varying number of connections in the transport layer may require a different approach than we use in the data link layer. Next, coming to the address. When an user process wishes to set up a connection to a remote application process, it uses specify which one is connect to. The method normally used to define transport address to which the process can listen for connection requests. In the internet, these endpoints are called the ports. We will use the generic term transport service access point. The analogous endpoint in the network layer are then called network service access point. The IP address are the examples of network service access point. The application process, both clients and servers can attach themselves to a TSAP to establish a connection to a remote TSAP. These connections run through NSAP on each host. To send the data to the destination, we need the address. That address is called as port address. The entity connects to the NASP, that is Network Service Access Point, in the network layer, whereas in the transport layer, application process is connected to the transport service application point. These are multiple process running with the host. Here, you are seeing the two host 1 and host 2, where you are connecting the process, a different process in a host 2, which is called as server 1 and server 2. The host 1, the process consisting of address, transport address, one port address 1208, whereas you're having port address of server 1 as 1522 and server 2 as 1822. The host 1 want to receive an information from the server 1. Then it is connected with TSAP 1522. The TSAP in host 1 1028 is connected to the transport connection. From that, it is passed to the network service access point. From that, it goes to the data link layer addressing. And similarly, at the host 2, it receives the address from the data link layer to the network layer. And the network layer considers the server 1 address 1522 and it connects to the server 1, where you're communicating between host 1 application process to the server 1 application process. The next example shows the initial connection protocol. Here you're connecting host 1 address to the different addresses in a host 2. Here you're connecting by using process server, because instead of giving number to each server's, process server is used. Here process server is used to listen the request, where the host 1 is sending the request. That request will be listened by the process server. Here you are establishing the connection by using process server. The user requests the server from the host 2. Some servers are used frequently. That's why instead of using different port addresses in a host 2, you are commonly using as process server. In the second figure, the process server, the address of the host 1 user is requested by the user to connect to the time of day server. Instead of process servers, you can also use directive or name servers. User is requesting the request to receive by name server, then that checks it with the directory numbers and it sends the TSAP number to the receive station. Similarly, as a process server, you are also having a directive or name servers also. This is used to overcome the previous one. Instead of you're connecting a single user to the multiple ports user, here you're connecting with an process server commonly. In the next slide, you are using connection establishment. Here, the the problem with the simple connection request and communication accepted exchange is that the network can lose, store, and duplicate packets. This behavior causes serious problems. To overcome this problem, you are going for delayed duplicates. The various ways to attack the problem are using a throwaway transport address, give each connection a connection identifier, or a mechanism to kill off aged packets, restricted subnet design, or hope counters, or timing stamping. Here, the primitives. Here you are seeing the three types of connection by using three-way handshaking. First figure indicates a normal operation where the host 1 is sending the connection request with sequence number X to the host 2. When host 2 receives the connection request from the host 1, it sends the acknowledgement to the host 1 with a sequence Y, and along with the sequence Y, it also sends the acknowledgement of X. After receiving the acknowledgement along with the sequence number, host 1 again sends the data to the host 2 with a new sequence and acknowledgement with Y. This is called three-way handshaking. Next figure shows the old connection request appearing out of nowhere. Here, host 1 already sent the connection request to the host 2, but the old duplicate connection request is received by the host 2 with a sequence X. This host 2 again sends the acknowledgement with the sequence Y along with the acknowledgement of sequence X. But host 1 knows that it doesn't send the sequence request to the host 2 now. That's why it rejects the acknowledgement of Y. Similarly, in figure she shows the duplicate connection request and the duplicate acknowledgement. In this also, host 1 already sent the connection request to the host 2. Here, host 2 is receiving some duplicate connection request which is lost previously. This duplicate connection request or the old connection request is occurred because of the because of the because of the mean because of the connection from one host to the another host may be of many ways. The receiving of the data from different way may take different time. Because of the delay, there may be an occurrence of old connection request and a duplicate connection request. Next figure, in figure C, the other intermediate duplicate connection request is received by the host 2. Then that sends the acknowledgement with the new sequence and the acknowledgement X. Then host 1 knows that it doesn't send any connection request and any data to the host 2. That's why it rejects the acknowledgement. In this figure, this figure shows the asymmetric release. Here you are having two types of connections. Connections of transport can be released in two ways, asymmetric and symmetric. If one of host terminates connection, then in both the direction, data communication will be transmitted is called asynchronous connection. In synchronous connection, if one of the host disconnects connection, then it cannot send the data, but it can receive it. This is the example of asymmetric release. Here, after the connection is established, host 1 sends a transport protocol data unit that arrives properly at host 2. Then host 1 sends another transport protocol data unit. Here, host 2 issues and disconnect before the second data arrives. This result is that the connection is released and the data is lost. The other type of connection release is synchronous connection release. The more significant release protocol is needed to avoid data loss is to use asymmetric release, in which one direction is released independently to the other one. Here, a host can continue to receive data even after it has send and disconnect data, that is transport protocol data unit. Asymmetric release does the job when each process has a fixed amount of data to send and clearly known when it has sent it. Once one can wait a protocol in which host 1 says, I am done. Are you done too? If host 2 responds, I am done too, goodbye, the connection can be safely released. It is here, it is in this figure, it is also called as four-way handshaking of connection terminal. The figure indicates the four protocol scenario for releasing a connection. In first case, it is a normal case of three-way handshaking, and the next is final acknowledgement lost. The connection release, in first example, the host 1 is sending the data release to the host 2 with an start timer. Then after receiving the data release from the host 1 to the host 2, then host 2 again sends the data release with the timer to the host 1. After receiving the data release from the host 2, host 1 releases the connection and releases the connection. After releasing the connection, it sends the acknowledgement to the host 2. Whereas in second figure, the host 1 sends the data release to the host 2 with a start timer. Host, after receiving the data release from the host 1, host 2 also sends the date, release with a start timer. Then host 1 releases the connection. After that, host 1 sends the acknowledgement to the host 2. But the acknowledgement is lost, and host 2 doesn't receive the acknowledgement. At that time, host 2 will wait up to the timeout of the start timer. After the timeout, it releases the connection. Here, disconnecting the connection between two users. After sending the data, we want to release the connection by host 1 or by host 2. The next figure shows the response lost, and D figure shows the response lost and subsequent data release loss. In this, so host 1 sends the data release to the host 2, but the host 2 sent the data release is not received by the host 1. Here the data release of host 2 is lost in intermediate. At that time, host 1 will wait up to the timeout. After the timeout of the host 1, it again sends that it understands that the host 2 doesn't receives the data release which is sent by the host 1. That's why again it sends a data request to the host 2. After receiving the data request from the host 1, again host 2 sends a data request to the host 1. After receiving the data release from the host 2, it releases the connection. After releasing the connection in the host 1, it sends the acknowledgement to the host 2. After receiving the acknowledgement from the host 1, host 2 is also releases the connection. In next figure, host 1 is sending the data release to the host 2. Host 2 sending the data request to the host 1, but it is lost in intermediate. That's why it waits for a timeout and again it sends the data request. Again, the data request which is sending by the host one is lost. Then host two doesn't receive the data request from the data host one. That's why it waits up to some timeout and after that it releases the connection. Similarly, at the host two also it waits the timeout of the for end rotations in timeouts and then releases the connection. The next is flow control and buffering. Transport layer manages end-to-end flow. If the receiver is not able to cope with the flow of data, then data flow should be controlled from sender's side. That part is done by transport layer. Data link layer is also doing flow control, but it controls flow of data between adjacent nodes in path from source to destination. Reasons for packet loss at the receiver is slow processing speed or insufficient buffer to store the data. Buffers are allocated at sender and receiver side. If the network surface is reliable, so every send data sent will be the delivered to receiver and will be buffered and processed at the receiver. So no need to keep the buffer at sender. But if network service is unreliable, that means it doesn't receive the acknowledgement properly and the receiver may not able to handle every incoming data, then sender should also keep a buffer where copy of data resides until its acknowledgement comes. In this figure, it shows chain fixed size buffers, chain variable size buffers, one large circular buffer. Here, even if the receiver has agreed to do the buffering, there still remains the question of the buffering size. If most TPDUs are nearly the same size, it is natural to organize the buffers as a pool of identically sized buffers with one TPDU per buffer, as shown in a fixed size buffers. If there is a wide variation in the data size, a pool of fixed size buffers presents problem. If the buffer size is chosen equal to the largest possible data, space will be wasted whenever a short data arrives. If the buffer size is chosen less than the maximum size data size, then multiple buffers will be needed for longer TDPUs with the attendant complexity. The another approach to the buffer size problem is to use variable size buffers, which is shown in the figure 2. The advantage here is better memory utilization at the price of more complicated buffer management. The third possibility is to dedicate a single large circular buffer per connection as shown in the figure C. This system also makes good use of memory, provided that all connections are heavily loaded but is poor if some connection is lightly loaded. Here, here the black color represents the unused space. Here the flow control means it's sending the speed is very fast compared to the receiver speed. To control that speed is called a flow control. To control buffer, transport layer manages buffer depending upon the overflow or the underflow. In circular buffer, data is used in circular way, that is in a queue. It informs that the different types of buffers are used. Next is multiplexing. Multiplexing is used to select one. Connection shades the network address. All the connection applications shades the network address. Whenever we are sending or receiving the data is called multiplexing. Responding the data is demultiplexing, where you are distributing into a many lines. There are two types of multiplexing, upward and downward. If only one network address is available on a host, all transport connections on that machine have to use it. When a data comes in, some way is needed to tell which process to give it to. In this situation, we are using upward multiplexing. If the user need more bandwidth than one virtual circuit can provide, a way out is to open multiple network connections and distribute the traffic among them on a round-robin basis, as indicated in Figure B. This shows the downward multiplexing. The both figures distributes four distinct transport connections, all uses the same network connection, that is the IP address to the remote host. The next is the crash recovery. Host and router are subject to crash. Router crash is easy to handle since transport entities are alive at the host. Routers are only intermediate nodes which forwards packets. They do not have transport layer entities. If host crashes, that is one client, that is one host is sending a file to the receiver host. The transport layer, its server simply passes data to the transport layer. While the transmission was going on, server crashes and comes up. The table initiated does not know where it was. Server sends a broadcast data to all hosts, announcing that it had just crashed and requesting that its clients inform it about status of all open connections. Each client can be in two states, one of two states, that is S0 or S1. If it is in S0, then it is no outstanding data. There is no outstanding data. If it is S1, you can say that there is one outstanding data. If data is outstanding, client should transmit it, but they can be different hidden situations. First one, if server has send acknowledgement and before it can send the data to the next layer, server crashes. In this case, client will get acknowledgement, so it will not retransmit and the data is lost by the server. If server, second point is, the second situation is if server first sends the packet to the next layer, then it crashes before it can send the acknowledgement. In this case, server has already received the data, client thinks data is lost and it will retransmit. Here, the receiving host, that is server, can be programmed in two ways. That is acknowledgement first and second one is write first. First acknowledgement and then write. Three events are possible at server. That is sending acknowledgement, sending packet to the next layer, and crash. Three events can occur in 6 different cases. That is which shown in the figure. Strategy used by the sending host, always retransmit. It always retransmits in figure which is shown here. The client can be programmed in 4 ways. One is always retransmit, another one is never retransmit, retransmit in S0, retransmit in S1. Here, the strategy used for sending hosts should always retransmit. First acknowledgement, then write, retransmit in S0, send 2 messages, acknowledgement of both received, no outstanding packet is present. Retransmit in S1, sends it 2 messages, acknowledgement of only one received, here the outstanding packet is present. When when a host receives a packet, it is bound to acknowledge that packet having the next sequence number expected if it is not the lost segment. When the TCP server crashes midway communication and restarts its process, it sends data broadcast to all its hosts. The host can then send the last data segment, which was never an acknowledgement, and carry onwards. This is about elements in data link, elements in transport layer. Thank you.